In this podcast, we'll go into how to identify types of redox reactions. So we've already covered what a redox reaction is. This is where it gets a little bit more simple. And we'll also predict products for redox reactions. As a friendly reminder, we have one element in a redox reaction losing electrons or being oxidized and one gaining. So again, you'll recall this image where A has 2 electrons and they are transferred to B. So A is considered oxidized. It is losing electrons, and B is considered reduced. It has gained electrons. So A has been oxidized, B has been reduced. And we also use the terms oxidizing and reducing agents. So if I'm oxidized, I am a reducing agent because I cause the other species to be reduced. And if I am reduced, I am an oxidizing agent. So again, we're just following those electrons. So before we get too far into this, I want to show you how all reactions are categorized. So we are focusing on redox reactions as a category of reactions. So we'll go over these 4 types of reactions, but metathesis are the other types of reactions. So that'll be a later podcast. So right now we're just going to focus on combination or synthesis, decomposition, single replacement or displacement, and combustion. All right, so in a combination or synthesis reaction, we have 2 or more elements combining to form a single compound. Okay, so I'm going to start writing a cheat sheet up here. I highly recommend that you write this down as you go because it makes identifying these really easy at first. So here we're representing single elements by A and B, and they combine to form a single product. So this is something that is unique to the combination or synthesis types of reactions. So they're pretty easy to identify because of that. So here we have element A and element B forming a bond. We can think of element A as a metal and element B as a non-metal, and they are forming the ionic compound AB. Okay, and they're doing this through a transfer of electrons. Your metal will lose electrons. Your nonmetal is going to gain electrons. So this is happening through a redox reaction. Our next type of reaction is a decomposition reaction, and it does exactly what it sounds like. It decomposes. So we're going to start with a single compound, and it will split into 2 or more species. So these could be 2 elements. It could be an element in a simple compound, 2 simple compounds. Kind of just depends on what you're dealing with. So here we have an example that was used previously with mercury 2 oxide. And I'm going to show you my cheat sheet real quick before we actually get into that example. I apologize. So we have a single compound forming 2 products. Again, starting with a single compound is your dead giveaway that it's a decomposition, because what else can happen? It can only split apart. So here's an example of what is happening. We have our mercury oxide, and it is splitting into mercury metal and oxygen gas. So here's our single element, and it is becoming, or I'm sorry, a single compound that's becoming 2 single elements. And it's doing this through the transfer of electrons. So both of these are starting out charged. Hg has a positive 2 charge, oxygen has a minus 2 charge, and they're both becoming neutral. And they do that through a transfer. Oxygen will transfer its 2 additional electrons, making it neutral, to mercury. Positive 2 plus those 2 negative electrons makes it neutral as well. Okay, our next type of reaction is called a single replacement or a single displacement or a single substitution. I prefer single replacement. I like abbreviating that with SR. So we have one element that is swapping or replacing another in a compound. So here's our single element, here's our compound. Okay, we're going to see our cations swap places. So here is our example. There's zinc, here's hydrogen. Now notice that these have charges already because they're in a compound, they're in an ionic compound, and the electrons have already been transferred. So what happens is my 2 positive charges, or my 2 metals, if you will, and I know hydrogen's like the worst example of this, but we'll say it's a metal. These 2 cations, or what have the potential to be cations, are going to swap places. So now hydrogen is going to be by itself, and zinc will be with chlorine. And to be with chlorine, it has to give up 2 of its electrons. Oops, we need another chlorine molecule in here. That's not even. 2 -1 charges. Okay, so in this case, we see your 2 cations, your 2 metals swapping places. So one was by itself. It's now going to transfer electrons and become part of the compound. And the one that was in the compound is going to be all by his lonesome. So single element and a compound. And notice that these two are going to swap places. Okay, our final type of redox reaction is going to be a combustion reaction. So in a combustion reaction, we always start with the same things, carbon, hydrogen, and oxygen. Okay, so any combination of that is going to start off on the reactant side, and it always produces the same thing, carbon dioxide, CO2, water, and energy. So this heat just represents that energy that's released. So this is where the redox reactions get a little bit tricky in our intro to general chemistry, because here we are talking about the gain or loss of oxygen. And remember, we talked about electron transfer specifically. I said, don't worry about this. Well, this is another example of where you would need to just trust me on this, and we'll get to it next semester. But we're going to have a gain of oxygen by some of these elements. So we start off with our hydrocarbon. So a certain number of carbons, hydrogens, burning in the presence of oxygen. Now, it doesn't matter how many carbons and hydrogens you have, as long as your octets are full. We'll talk about that next semester. But they always form the same products. They're always going to form a certain amount of CO2 and H2O. And once we balance that equation, we'll find out how many carbon dioxides and how many waters are formed. So the tricky part of this is that this redox reaction looks a lot like a single replacement, because you have a single element and you have a compound. So every time you think you might have a single replacement, you might want to ask yourself, is this only carbons and hydrogens and oxygens? If so, it's not a single replacement, it's a combustion reaction. All right, so again, to reiterate, we have covered these 4 types of redox reactions. So remember that redox is the transfer of electrons, or we can think about it as the gain or loss of oxygen. Okay, and this part is important for combustion, but it really comes up more in organic chemistry next semester. In future podcasts, we'll worry about metathesis reactions, but that's not your worry right now. Okay, so we've learned about redox reactions. We've learned about the types of reactions. We can actually use the classification of your reactants to predict products. And we do this based on determining whether the reaction is a single replacement, a combination, a decomposition, or a combustion. Here are the steps you're going to want to know. These are the steps I would have out in front of me until I have them memorized and I don't have to reference them anymore. So we will start off by reading this, and then we're going to write out neutral formulas for each reactant. Okay, so solid sodium reacts with aqueous aluminum carbonate. So whenever you see solid sodium, they're really just emphasizing that sodium is not with anything else. It's all by itself. Reacts with means plus. And aqueous tells us the state of matter, which we care about. Solid's a state of matter too. I mean, we can add that in if we want to, but that's not really your concern right now. We'll deal with that later. Aluminum carbonate. So I know this is aluminum with a 3+ charge, and carbonate's a polyatomic ion with a 2- charge. So I'm going to drop and swap those. So Al2CO3, and I'll need parentheses to have a 3 on the other side. And it's really important to check your charges, because we're going to be swapping elements around, and you want to make sure that you started with a neutral compound each time so that you get the correct subscript. You start off with the correct charges. All right, so this looks to me like a single element and a compound. I'm sorry, we said that was aqueous. I also said it didn't matter though. Okay, so we start off with a single element and a compound. This to me looks like a single replacement reaction, where I take those cations or those metals and I swap places. But I want to ask myself first, because I don't want to be fooled, is this carbon, hydrogen, and oxygen only? Because if so, it's a combustion. Nope, it's not carbon, hydrogen, oxygen only, so it's not a combustion. So what I'm going to focus on now is I'm going to swap these two cations. So aluminum is now going to be by itself, so it's now neutral. And sodium, and I'm going to put my charges on here, is now with carbonate. And I want to make sure that I drop and swap, creating a new neutral compound. So I can go ahead and erase my charges. It was a +1 on sodium and a -2 on carbonate. Okay. So, oh my gosh, I skipped all these steps without even identifying I was doing these steps. So I wrote out my neutral formulas. I already said it was a single replacement. I predicted products based off rules. I wrote neutral compounds. The last step is my favorite. We are going to balance. 1 sodium here, 2 over here. Oops, we'll put a 2 here. 2 aluminums, 2 aluminums. Now I can count carbonate as a whole as long as it stays as a CO3 on both sides, which it does. So here I have 3 carbonates, and here I have 1. So I'm going to put a 3 in front. However, that fixes my carbonate issue, but it creates a whole new issue for sodium. Now I have 6 sodiums. So I'm going to go back, and I would erase this for you, but I don't know if you'll be able to see it once I erase it. And I'm going to replace that 2 with a 6. So that now I have a balanced reaction.